So in this section we will analyze the effect of blocking and how to assign treatments to the different blocks, and we will need a little bit of mathematics to be able to fully understand the effect of the blocking on the analysis and the implications of having different block configurations. Okay, so the idea of blocking is to reduce the variance due to some known but uninteresting factor. So let's say that we are interested in comparing treatments A and B. We know that the results will depend on male and female, so we will use male and female as blocks, but we are not interested in the differences between male and females, but we are interested only on the differences between treatments. So if we have two treatments and these blocks, and we apply all treatments to all blocks, then this is the ideal situation. Blocks see all treatments. But let's say that for some reason you cannot do, you have three treatments, but you cannot do more than two measurements on the blocks. So now you can have experiments like this one, or design like this one. So males will see A and C, females will see B and C, and then you have the common treatment C that will help you to relate the effect of A and B. There is an assumption here. So the assumption is that the effect of A, B and C are similar, and they use the same kind of cellular and molecular mechanism. So the results, by seeing C in common, you can extrapolate what would be the effect of A onto the other block. We will see that. But there are situations in which this assumption is violated. So let's say that we are talking about hormone treatments. So these hormone treatments, these A, B and C are different hormones, and let's say that they have an effect on different organs. And let's say that some of the hormones, they have an effect on ovaries, let's say. So let's say that A or B has an effect on ovaries, and then we see some effect on the females, but when we apply the treatment B to males, we don't see any effect, because we cannot extrapolate what we have seen in females to males, because males do not have ovaries. Okay, but assuming that the mechanism of action is the same, then having C in common will help us to translate A to females and B to males. And the more we have in common, so let's say that we have treatments A, B, C, D, so, and you can only do 3 per block, then you can, the more they have in common, here we have only 1 treatment in common, here we have 2 treatments in common, so that will help us to make a better transfer from A to females and B to males. And you may think of these blocks as male-female, but you can also have, I don't know, the day of the experiment, so that in principle the mechanism of action is the same. It wouldn't matter what is the day, and the differences between days may be caused by temperature, different humidity, different whatever, different person doing the experiment, but you assume that you can transfer the effects measured on one day on one of the treatments to the effects that you would have measured of A in the second block if you could have done it. Okay, now it is where we need the mathematics to be able to analyze these blocks. So let us analyze the simplest example, that is this one, in which all blocks receive all treatment, and then the data he assumed that it is generated according to this equation. So our observations will be a general mean plus something that depends on the block plus something that depends on the treatment plus some noise. And let us assume that the design is balanced and there are k replicates for each one of the block treatment combinations. So this A has k observations, this B has k observations, and all of them have k observations. So now we can compute the sum of all the observations in block 1, the sum of all observations in block 2, the sum of all observations in general, all observations in treatment A and treatment B. And then this will be random variables, and we can compute what is the expected value of these random variables. So this sum is the same as the expected value. This sum on group 1 is the same as the sum of these two. So the expected value here will be k times, because we have k combination, k replicates, of the expected value of this sum of this treatment, that is mu block 1 plus dA, and then the same for the other one. So we can at the end we can see that the expected value of this is this one, and we can do it for all the others. So this is the expected value for the sum of the first block, for the second block, for all of them, for treatment A and for treatment B. And then we know already our least squares equation system matrix, so we can solve for which are our unknowns. They are mu, b1, b2 is not an unknown because we can put it as a function of b1, and then ta and tb again is not an unknown. So we have 5 equations because we have 5 sums, and this is the system matrix, and these are our unknowns, and these are our measurements. And you may reduce this equation system. For instance, you can divide this line by 4k, and now you subtract this line from this line 2k times, and well, you reduce this left hand side to this thing, and then the right hand side reduces to this, and you have two equations that are important. This one here, you have 0 0 0, meaning that the left hand side is 0 and the right hand side is this one, but this is also 0. You may go to here and you may check that this one plus this one minus this one divided by 2k is 0. So you have 0 equals 0. So in practice what you have is an equation with 3 unknowns and 3 equations, because 2 of them it is 0 equals 0. That is a tautology, it is always true. Okay, so now we can estimate the different contributions of the model, and yeah, so we see the estimate of mu is the overall sum divided by 4k. The estimate of B1 is this thing, but this thing is the average of group 1 minus the total average. That is the kind of rules that we have already introduced at the beginning of the course. So if you want to see what is the effect of a block, you compute the mean of that block and then subtract the overall mean, and the same for the treatments. But this is true under this assumption, under the assumption that all blocks have seen all treatments. And once you have B1 and TA, you can compute B2 and TB. Okay, so and then you can see that the same happens for, so B2 is minus B1, that is this thing, but this is exactly this. So the same rule of computing the mean of the block minus the overall mean applies for B2, and it also applies for TB. And if you want to test whether there is a significant difference between the treatments, you will compute this difference, which is the same as making this subtraction between the mean of group A and the mean of group B, and then the variance of this is the variance of this one minus the variance of this one. So each one of the measurements has a given variance. So this is the variance of the residuals. But because in A you are measuring 2k individuals, and this 2k comes from block 1 that has k and block 2 that also has k. So you will be dividing by 2k, and the same for B. So the number of replicates that you need to test to make a two-sided hypothesis to see if there are differences between A and B is given by this sample size calculation that we already know how to do it because of and you are referred to the course on sample size for making this calculation. But here the main message is given what I want to compare, I can compute how many replicates I need in each one of the cells to be able to detect this effect size delta, to be able to detect changes of a given size with a given confidence level and statistical power that are probabilities related to the probabilities of making false positives and false negatives. Okay, so let's analyze a second example. So in the second example, we have only one treatment in common, and block 1 has not seen B, block 2 has not seen A. Our equation of how the measurements are generated is still the same, but now when we compute the expected value of the sum of block 1, we have the expected value of the first treatment plus the of treatment A plus the sum of the treatment C. So it is this thing, and this thing is equal to this. So it is the same as we had before plus a new term that we have shown in red, and the same happens for the sum of the second group, for the overall sum, for the sum of group A. So A we have this, for B we have that, and for C we have that. So we have marked in red the differences with respect to the previous situation, with respect to this situation here, in which the blocks they saw all treatments at the same time. Now we set up our equation system, and in our equation system we know that C we don't have to compute, because once you compute A and B you can compute C, and you don't have to compute B2 because once you have B1 you can compute B2. And again, after you simplify your equation system, again you have two equations that are equal 0 on the left hand side, but they are also equal 0 on the right hand side. So if you compute all these sums, you do it using these relationships, then you see that this side is 0 and this side is also 0. Okay, so we have a consistent equation system in which we have 4 equations and 4 unknowns and 4 equations. And now what is interesting is that for instance we want to compute the mean. So what is the intercept? What is the estimate of the intercept? The intercept now is much more complicated. It is the average of A plus the average of B plus 4 times the total average divided by 6. We can compare two the average before, so to the estimate before. The average before was the intercept was the overall, simply just the mean of all observations, which made perfect sense. Now it is much more difficult. It is technically correct, but we couldn't have come to this intuitively. And the same happens for the effect of the block. So the effect of the block, before it was simply, we had it somewhere here, I think. So the effect of the block was the average of the block minus the total average, which was very easy to calculate. But now the effect of the block is 4 times the average of block 1 minus the average of group A plus the average of group B minus 4 times the total average divided by 2. So again, they are totally correct. They are unbiased estimates of the true effects of B1, TA, TB, but because the blocks are not balanced, the blocks do not see all treatments, now it is much more difficult. And it has a consequence. So when we are comparing group A and group B, that is this thing, the variance of this is, okay, so we have to compute the variance of this. So it is 4 times, so the coefficients in front have to be squared. So it is 4 times the variance of this plus 4 times the variance of this plus 16 times the variance of this and 16 times the variance of this. And you count how many individuals you are averaging in each one of the groups. So in the average of group A, we are only averaging k individuals. So this will be sigma divided by k, and the same for group B. And in group 1 we have 2k individuals because we have 2 treatments, so we have 2k. So this is 2k, and the total average we have 4k. So in total this comparison has a variability that is 20 times the variability of the residuals divided by k. Let's say that now we want to compare A with C, and you do the same kind of analysis, and now the variance is only 6 times the variability of the residuals divided by k. So that means that when you are making pairwise comparisons, comparing treatments that have been shared in the same block, it is much easier because it has a lower variance. So A with C has a lower variance than when we compare A with B, because A with B, they were never in the same block, and we are making this comparison through an intermediate C that also introduces some variance. So that is why the variance here it is much larger. So yeah, as a message, the comparisons within the same block are more precise than when you are comparing treatments that are on different blocks. And we will not analyze the third example, but we can extrapolate what we already know. The more treatments we have in common between the different blocks, so before we only had C in common, now we have C and D in common, so that translates into a smaller variance of all the tests. So when we compare A to C or A to B, they will have a smaller variance the more treatments that these groups have in common. Okay, so let's analyze this other possible design, and let's say that in block 1 we have 4 treatments, but for some reason we can only do 2 treatments per block. So we have in block 1 A and C, and block 2 we have B and D. So we see that there are no treatments in common. So does it cause any problem? Okay, we do the same kind of analysis that we did before. So we compute what is the expected value of each one of the sums, group 1, group 2, the overall sum, group A, B, C, and D. And then we set up our equation system for the least squares, and we simplify this one, and then let's see what we have. Okay, so we have this equation 0 that is equal 0. So okay, so that is good. All these values here, they are 0. That is good. But then what we have is we have three equations. How many equations? 1, 2, 3, and 4. So we have 4 equations different from 0. So whose coefficients are different from 0. But we have 5 unknowns. So that means that with 4 equations we cannot solve for 5 unknowns. The first four variables will be a function of the fifth one. So that means that we cannot relate, we cannot analyze this data. So because they don't have any parameter or treatment in common, we have completely spoiled our experiment, because once we have it, we will have a lot of measurements, and then we cannot determine the fifth variable. So we have to sacrifice something, and what you have to sacrifice here is estimating the block. So if you don't estimate the block, now you have 4 equations with 4 unknowns. But the problem is that you are confounding the blocks with the treatment. So if block 1 has an effect, it is confounded with treatments A and C, and the same for block 2. So this is an incorrect design from the very beginning. Yeah, so of the 40 designs of this section, the only one that has an orthogonal matrix is this one, so in which all blocks see all treatments. So orthogonality keeps the calculations very simple. So we have seen that when all blocks have all treatments, then it is very easy to say what is the effect of the block, what is the effect of the treatments. We have seen that. And otherwise, if the data is not orthogonal, then this was this case, which the estimates of each one of the parameters was much more difficult, and we have to rely on least squares to solve this problem. And also non-orthogonality is not a major drawback. It has an impact on the comparisons, so we have seen already that. So the comparisons within the same block will be easier than the comparisons among blocks. So this is same block, this is different blocks, but it has an impact on that, but it is a kind of minor impact. There is something much more important, that is the balance, and the balance will be the topic of the next section.